Welcome back to your physics notes. So what we're going to look at now are some Newton's second law situations. So on the AP exam, I can pretty much guarantee you, if you're taking C, that one of your problems will be an in-depth Newton's second law problem. If you're taking AP Physics 1, you have a very good chance of this being one of your free response problems, and you will have lots and lots of multiple choice questions about this. So the nice thing about these problems is they all pretty much start the same way, and you have the same basic logic for solving them. Okay, so what you're going to want to do is let's take the three most basic kind of situations. So the first one is when you have a ramp, right? So let's say you have a ramp and you have a block on that ramp. They will always pretty much tell you that it makes an angle theta. They might give you an angle, but you need to be prepared to do this with absolutely no numbers, all algebra based. They might tell you that it has a mass m. They might give you more information. It might be moving. It might not be moving. But remember, what it's doing doesn't matter. All that matters is whether you can identify whether it's accelerating or not and in which direction. Okay? So let's say in this case, acceleration equals 0. So that means that the block is at rest. Well, I don't know that it's at rest. Let's say it's at rest. Velocity equals 0 also. On the ramp, okay? And acceleration is 0. So they might ask you to find the coefficient of static friction. They might ask you to find the angle. They might ask you to find all kinds of stuff. It doesn't matter. What you're first going to do is start the exact same way, and that's with a free body diagram. And in fact, the first thing they probably ask you to do is to draw the forces acting on the block on the dot below. They'll state something like that. So to draw a free body diagram, remember you identify the objects that it's interacting with. We're talking about the block. It's interacting with the earth through its weight. It's interacting with this table or the plane with a normal force. And then also, since the only other thing I can identify is the surface and the earth, I need another force in order to achieve this A equals 0. You can see that the normal force or the weight, however you want to break it down, would have a component that goes in this direction over here. So I need something pointing up this way, and that would be static friction. Remember, with friction, you always have to ask yourself, which way does it need to point? There is no standard direction other than parallel to the surface, but whether it's up the surface or down the surface depends on the situation, okay? That is my answer to the first part if they want me to draw a free body diagram. I do nothing more to that. All right. Now, after that, they're probably going to ask for something else. Find theta or find the coefficient of friction or something like that. I would now apply Newton's second law. So to apply Newton's second law, I would need to write the sum of the forces in the x dimension r and the sum of the forces in the y dimension r. And then I would plug those forces in there, whatever they are, and that's equal to m ax. Same thing down here. M-A-Y, and you remember that since my acceleration is 0, these are each going to be equal to 0. So I can kind of do that. All right. So now this might look a little confusing. I apologize, but this is the general format where you write this out and then you plug in your forces right there. All your forces in the y dimension go right there, and you add or subtract them based on whether they're positive or negative, and it's equal to MA, but in this case, A is 0. Okay. So what I would need to do this is break down one of these forces into its components. Anytime you have an object on an inclined plane, you can do it however you want, but my recommendation is to make your axis that you're looking at, your dimensions, tilted at the same angle that the inclined plane is. And if you do that, think about it. Look at your forces and look at this. How many of your forces are now in 2 dimensions? And the answer is only one, just the weight. F sub s, friction, points in the positive x direction. The normal force points in the positive y. So you only have to do one force for your force resolution diagram. So to do my force resolution diagram, let's basically start with your free body. You have N. I kind of messed up that angle, but that's okay. You only have to break down the one force, weight, that's in 2 dimensions. Now, you might be asking how I got that. If I were to draw this, that's my weight vector right there. If this angle is theta, and I draw another line down like this, which is essentially what I'm doing in this triangle right here, you can see that this triangle and this triangle are congruent. And this angle right here is the same as that angle right there. And I challenge you to kind of prove that and look at why I state that it has to be like that. You're going to want to look at this angle to make that determination. So that's theta, and I said that this was mg. So that means that this is mg cosine theta. That's the adjacent side. And this is mg sine theta. That's the opposite side. So now, using my force resolution diagram, okay, I can plug in my forces right here. In the x dimension, which I said was up and down the ramp, I have 2. I have static friction and mg sine theta. So I can put F sub s, which I said was in the positive direction, minus mg sine theta. And then in the y dimension, I look at which forces are in the y, and there's only 2. There's mg cosine theta and n, and I said that the direction of n is the positive y, so n minus mg cosine theta. All right, so I've accounted for all of my components of my forces and my forces, and I know that they both are equal to 0, so I can kind of rewrite this if I wanted to. So now I've got static friction. I could rearrange this as equal to mg sine theta, and n is equal, let's write that n better, equals mg cosine theta. And now maybe they want me to find mu. Remember that the force of static friction is less than or equal to mu times n. So using what mg sine theta is and what n is, you can figure out what mu is. You could even find the angle if they ask you for that. This is the basic way to solve these problems. You start with F free body diagram, and then you use Newton's second law. Now, very similar. You could have a multiple rope tension situation. So this is a diagram from an AP physics problem a few years ago, where you have a monkey. You have that. We did one like this. First step, free body diagram. So they tell me that the monkey's at rest. He's sitting there hanging from these ropes. Interaction 1 is between the monkey and the earth. Interaction 2 and 3 are between the 2 ropes, and they each have different angles. This is 30 degrees. This is 60 degrees. If I draw kind of a horizontal line here, I'm going to call this TA because they call that rope A. I'm going to call this TB because they call that rope T. So that is my free body diagram. That's it. I shouldn't probably even have these angles on there, but those are the 3 forces acting on the monkey. That's it. Next step, force resolution diagram. You start with the exact same thing, mg. This is TB. But again, I'm going to break this down into its components. And if this is 60 degrees, which I'm just going to call it phi, just so I don't have to write numbers, and then this one is TA. I'm going to break him down into his components. And let's call this angle theta. So I have angle phi, angle theta, okay, which in the problem are 60 and 30, doesn't matter. Now I break them down into their components. Well, what is this? This is the opposite side of that angle. So that's going to be TB sine of angle phi. This will be TB cosine of angle phi. This is TA cosine theta. And this is TA sine theta. So now I don't have to look at these vectors anymore. I look at their components. Newton's second law, sum of the forces in the y dimension. And again, these should add up to 0 because my acceleration is 0. Look at your positive y ones. Let's say TA sine theta plus TB sine phi. And then mg is in the negative direction. And those add up to 0 because my acceleration is 0. Now I could do the same thing for the sum of the forces in the x dimension. Look in the x, I only have 2. Okay, so TB cosine phi minus TA cosine theta equals 0. And the one thing I forgot to do earlier, which I kind of just took in the default direction, is you want to identify which way you're saying is positive and negative. Okay. So there you go. Now you could use this. Let's say, if I remember in this specific problem, they wanted you to find TA and TB, which now you have two equations, so you could solve these using a system of equations to solve for both variables, et cetera, et cetera. You can simplify it by plugging in your numbers, and you can get rid of some of those. So that's the basics of how you do it. A multiple tension problem. Now, this one is a little different. Now we have multiple objects, okay? So I would need to draw free body diagrams for each object. So if I tell you that right now these objects, let's say, are at rest, right? So, and the acceleration is 0. I would want to name these. So I would call this, let's say, object A, B. You could call them M1, M2, but you would do the same thing. You would have a picture. There's your rope. There's your blocks. Let's call that one M1. Let's call that one M2. Probably what they're going to want you to do is draw the forces on M1. So what's it interacting with? What objects? It's interacting with the Earth. That's going to be M1G. It's interacting with the surface and the tension. Well, the tension is going to be along the rope, so call that T. And now the surface, there's going to be a normal force, which is perpendicular to the surface. And you ask yourself, does there need to be any friction? Because there could be friction. They didn't say it was frictionless. And the correct answer is I don't really know yet. I would need more information. Friction could point that way, right? Which it probably does based on the situation. But friction could be 0 because, remember, static friction is an inequality. So it could be as small as 0, and it could go up to a maximum of that. So I don't really know based on the information yet. They would probably give me more information. Now, the hanging block, hopefully, is significantly easier. You can see it's not touching the surface. So the only objects it's interacting with are the Earth and the rope. And since acceleration is 0, I know these vectors must be the same length, and mg is equal to t. Now, for this, you would again apply Newton's second law. You would break this down into two components. And which vectors you have to do depends on which way you draw your dimensions. I would probably say positive x, positive y, which means that n and t are one dimension. This is in the positive y, this is in the positive x, so I need to break down mg just like any other inclined plane problem. And then you would write Newton's second law. So those are significantly challenging, and I realize that, and I breeze through it really quickly, but we'll get lots of practice in class and in your problem set. But you will master these types of problems soon, and you'll see that it's pretty repetitive. Free body diagram, force resolution diagram, and then you apply Newton's second law. Good job.